Let us go back to two previous examples. The first one is this differential equation and the second one is a similar one. Let us first note that this equation is not exact, and the equation of course is y dx plus 2x dy equal to 0. We have seen this before also. Why is it not exact? It is of course of the form m dx plus n dy equal to 0, where m is y and n is 2x. So if you calculate del m del y, then you are getting 1, whereas del n del x is 2. And at no point x comma y in the plane R2 are these two equal. They are never equal, and that is why the differential equation is not exact anywhere, in particular not inside any rectangular region. But then we have this equation also, which actually is obtained from that one by multiplying both sides by y. So that way we get y square dx plus 2xy dy equal to 0. This one however is exact, because if you do the similar calculation here m is y square and n is 2xy. So del m del y is 2y and del n del x is, here you are differentiating partially with respect to x, so y is considered constant and you get 2y. So again you get 2y, and this is true for all x comma y in R2, and that is why this equation is exact in any rectangular domain in the plane. So the non-exact equation turns into an exact equation but when we multiply it by something. So when that happens, that thing by which we multiply is called an integrating factor. So let us see the general definition of an integrating factor. So this is the definition. The original differential equation m dx plus n dy equal to 0 is, say, it's not exact in some domain D. But when we multiply it by some function of x and y, say mu of x comma y, then this becomes exact in D. If this is the situation, then this function by which you are multiplying is called an integrating factor for this original differential equation. Let's see one example. Already we have seen one elementary example, but let us see another one. So this is the example 2.7. So here we are considering this differential equation. 3y plus 4x y square dx plus 2x plus 3x square y dy equal to 0. So if we write what m and n are in this case, then m is this and this is n. So then we calculate these partial derivatives. Del m del y, here we are differentiating partially with respect to y, so we are going to get 3 plus 8xy, and differentiating this one partially with respect to x would give us 2 plus 6xy. Now unlike the previous case where we got 1 and 2, here we cannot straight away say that for all x and y these two are going to be different. There is a possibility for having equality at some points. Let's see where these two partial derivatives become equal. So the partial derivatives are different except at those points x comma y in the plane at which these two expressions are equal, or in other words at which 2 times xy plus 1 equal to 0. Now you can check that this actually is a curve. Okay, it's not any region having some non-zero area. It's a two-dimensional curve. So at such points on this curve only these two partial derivatives are equal. But then the differential equation is not exact in any rectangular domain, which demands that we have exactness within the interior of a rectangle, because exactness is possible only at the points on a curve. So exactness is not there in any rectangular region. no matter how small you choose the region. And that's why we cannot apply either the standard method or the method of grouping to solve our differential equation. But what if we can multiply this equation? You don't have the equation here, but it is just this, by something that will turn it into an exact equation. Let's see. Take our mu to be x square y. So if we multiply the original differential equation by x square y, then it gets turned into this 3x square y square plus 4x cube y cube dx plus 2x cube y plus 3x to the power 4 y square dy equal to 0. So now you calculate these things, these partial derivatives. You do understand that here this m now is this, it's not that previous m. N also is this one. So differentiating this partially with respect to y, what are you going to get? Y square will get turned into 2y. So that way you are getting 6x square y. And if you differentiate this one partially with respect to y, y cube will become 3y square. 3 times 4 is 12, x cube y square. On the other hand, if you differentiate this partially with respect to x, then x cube will give you 3x square. That 3 and this 2 will give you 6. So 6x square y again we are getting. And this one here, x to the power 4 will give you 4x cube. 4 times 3 is 12, x cube y square. So yes, this time we are having equality for all points in the plane. So the new differential equation is exact because of this condition being true everywhere in the plane in any rectangular domain D in the plane. And that is why you can apply either the standard method or the method of grouping to solve this equation. So then you will get a one parameter family of solutions. But now a question arises. Are these the solutions of the original differential equation? We actually don't know. Or are there extra solutions within this family of solutions, which are solutions to this one but not the original one? On the other hand, are we losing solutions? Maybe solving this equation you won't actually get original equation solutions, all of them. Okay, so we don't really know how to answer this at this stage. But even before those questions arise, a more fundamental question arises. Actually, there are two questions. Given a differential equation that is not exact, is it always the case that there is an integrating factor? If not, then what are the equations for which integrating factors exist? That is the first question. And the second question is this. Say by some means you come to know that there is an integrating factor. But then how to find one? For example, here we seem to have just magically thought of this x square y. Where is this x square y coming from? How do we first of all know that it exists? And then how to find it? So these questions won't be answered at this stage. We will address them later. Instead, what we will do, next we are going to start studying the two other types of first order equations that we mentioned in the beginning. We have already seen some things about exact equations. The next two types are separable equations and linear equations, and for them we will see that integrating factors really are there. Okay, when the equation is originally not favorable for immediate solution, you can multiply the equation by something to make it integrable, and that is why in fact we call these multiplying functions integrating factor. They make the equations integrable or solvable. And these questions that we discussed here with this example, they will be addressed in the next chapter, I think, next chapter or not in this chapter. I don't think in this chapter they will be addressed. They will be addressed in the next chapter or somewhere after that. So with that, this section ends, and after that we have exercises. So we will solve the exercises and then only we can start separable equations, and then after that linear equations. So see you next week on the same day with exercises and their solutions. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.